This lecture continues our discussion of optimization problems. And what we saw here in the first two examples from the previous lecture is that we need a primary equation. Okay, that's what we're going to apply the calculus to. And then what we're generally going to see is that our primary equation is going to involve two variables. So we're going to need this secondary equation next, okay? Once we have this secondary equation, we're going to be able to solve it for one of the variables, plug it back into the primary equation so it's in terms of one variable, and then apply our calculus. Okay, so I did the first example here was finding the product of two numbers such that the sum is a minimum. This one was maximizing area given some perimeter constraint. And now let's try this one here. Let's find the point or points on the graph of the function f of x is equal to x squared that are closest to the points 0 to the point 0, 3. So look. Here's the graph of x squared, right? Here's the point 0, 3. I want to find the point wherever it is. I don't know what exactly those points are, okay, that are closest to this. So what I want to do, all right, if I want to find the point closest, is I want to find the minimum distance. Okay, I want a min distance. All right, so that's our primary equation. Okay, the distance formula is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared, right? That's the distance formula. All right, well, you know, what exactly is our secondary equation here to plug in here? Well, there's actually two things to plug in. We know the point, right? So the point, the x1 comma y1 is equal to the point 0, 3. That's one of the points. Now we don't know the other point, right? So the x2, y2, all right? That's going to be the corresponding x value and the corresponding y value. Okay, well the x value is going to be whatever it is. And what is the y value? The y value is given by the function. All right, that's what that's what y is equal to. It's x squared. So that's where that's going to get replaced with y. So watch this, okay? Distance formula is equal to x minus 0 squared plus y2, well, the y value is x squared minus 3 squared. So I just have to clean this up a little bit here. So x minus 0 squared is just x squared plus, when I square this, I end up getting x to the 4th minus 6x squared plus 9. So even just cleaning that up a little bit, it's the square root of x to the 4th minus 5x squared plus 9, because the x squared minus 6x squared. Now here's the thing that you can actually do to make this easier. This equation, this distance equation, is minimized whenever what's underneath the square root is the smallest number. So d is minimized when, if I just define this function here, f of x is equal to x to the 4th minus 5x squared plus 9 is minimized. Okay, so don't worry about the square root here. All right, because if you were to take the derivative of that, then it involves a chain rule and it gets very messy. So look, moving over here, we're just going to apply the concepts to this function. F of x is equal to x to the 4th minus 5x squared plus 9. Well, the first derivative here is 4x cubed minus 10x. So you got to find the critical values of this, right? So, factor it, factor out of 2x. You're left with 2x squared minus 5. When does this equal 0? Well, when 2x is equal to 0, so when x is equal to 0. Solve this, right? You'd add the 5 over, divide by 2, take the square root. Well, you'd get minus square root of 5 halves, or the square root of 5 halves. Okay, so you have 3 possible values. And like, here's the thing. You don't know which of these are max or mins. So that's where you throw in the second derivative. So you want to find the min. So look, if you take f double prime of 0, okay, that's less than 0. So that means 0 is the max. Ugh. Okay, you don't want that. Okay, that's no good. But if you take f double prime of both these, because you're squaring them, you end up getting the same value. Both of those numbers are greater than 0, right? Like when you square root, sorry, a little mistake there. You get, 5 halves times 12 is 30 minus 10 is 20, so it's greater than 0. So these are the min. And that's why you can see there's 2 points here. All right, so the 2 points, or the points are, the first one is minus square root of 5 halves, comma, f of, minus the square root of 5 halves, and the other one is square root of 5 halves, comma, f of the square root of 5 halves. So a little bit trickier on that one. Not as straightforward. All right, let's try another one here. So a rectangular page is to contain 36 square inches of print, okay? But now here's the thing. That's where the print goes, okay? The margins on each side are to be 1 inch. Find the dimensions of the page so that the least amount of paper is used. Okay, least amount of paper used, all right? We want to min something. So for this, I actually find that a drawing helps, right? So a rectangular page. Okay, this is the print area, X and Y. And then what happens here is then they have 1 inch margins around it, okay? So this is 1 inch, this is 1 inch, this is 1 inch, and this is 1 inch. So the total length down here is actually x plus 2. And the total width up here is y plus 1 and 1 is y plus 2. And so we want to minimize this total area here. This is the total area we want to minimize because that's all the paper. So that's our primary equation. Right? It's the area of this total paper here, which is x plus 2 times y plus 2. Well, what's our secondary equation? Well, we know that this print area has to be 36 square inches, so it's x times y is equal to 36. Well, solving for y, you get y is equal to 36 over x, right? So look, now you can plug it right in. Boom. Area is equal to x plus 2, and now instead of y, you get 36 over x plus 2. Right, so let's distribute here, right? X times 36 over x is just 36. X times 2, so plus 2x, excuse me. 2 times this becomes plus 72 over x, plus 4. So 36 and 4 is 40, but that doesn't matter here. If I take the derivative, they both go away. So this ends up just being 2 minus 72 over x squared. right, so now what I want to do here is I want to apply the calculus to this right here. So I'm going to look where the first derivative is equal to 0. See if I got any critical values. Yeah. Add this over. Cross multiply. Divide by 2. And look, when you take the square root here to solve, you're only interested in the positive, right? Because you can't have a negative length or width here, so that's why I'm only writing the 6 here. And then look, again, if you apply the second derivative test, this ends up being negative 2 times negative 72 gets me positive 144 over x cubed. And look, when you plug 6 into this, it's greater than 0, right? For x is equal to 6. So you have a min. So that, the value of 6 is equal to the width here, okay? So you have to be very careful here. Find the dimensions of the page, the total page. Thus the width, the total width is x plus 2, which is 6 plus 2, which is 8. Okay, this is inches. And the length is equal to y plus 2. Okay, don't, just be careful you don't just grab x and y. Well, y is 36 over x, which is 36 divided by 6 plus 2, which is 6 plus 2, which gets me also 8 inches. So pretty crazy. Like, hopefully you're seeing here, like, the trick basically is like, once you find the two equations, the primary and secondary equation, the arithmetic and the calculus, hopefully isn't too challenging. And you can see, the process here, right? Take the derivative of the primary equation, find the critical numbers, use the second derivative test to see if you have a max or min. All right. Let's try this one here. A farmer plans to fence a rectangular pasture adjacent to a river. Okay, the pasture must contain 100,000 square meters in order to provide enough grass for the animals. So this is, basically where the animals are going to graze is what's going on here. Okay. And it says no fencing is needed along the river. Okay. What dimensions will require the least amount of fencing? All right. Well, look, here's the river. And no fencing is required along the river, obviously. So this will be our width. We're looking for that. And then y will be our length. Well, look, what is this farmer trying to minimize, okay, right? They want to use the least amount of fencing, okay? That's the perimeter. That involves the least amount of fencing. So it's 2y. The perimeter in this case is equal to 2y plus x because there's no other x along the river. So that's the primary equation. And then look, they tell you it must contain 1,000 square meters. So the secondary equation you're given is the area, right? So it's 100,000 is equal to x times y, or y here is equal to 100,000 divided by x. So look, you're literally just going to plug this in, okay? And I'm going to move it over here to the right. All right, so then our perimeter is equal to 2 times y. Well, 2 times 100,000 would be 200,000 over x plus x. Let's take the derivative. Well, bring this up as x to the negative 1. You get minus 200,000 all over x squared plus 1. Set that equal to 0 and solve. So add this over. You get 200,000 divided by x squared is equal to 1. Cross multiply, you get x squared is equal to 200,000. And x is equal to the square root of 200,000. And you don't need to take the negative here, right? Because you're, excuse me, you're finding a length and width, so they have to be positive, okay? So then look, again here, right? Look at the second derivative. If you take the second derivative of this, you end up just getting 400,000 over x cubed, which is greater than 0 for when you plug in the square root of 200,000, obviously. So what that means is you have a min, right? So we have used the least amount of fencing to meet this area restriction. Okay, so thus the dimensions are we have the width, which is the square root of 200,000 meters. And then the length, which is y, well, that's 100,000 divided by the square root of 200,000. I'll leave it like that, meters. Again, find those primary, secondary equations, and boom, you'll notice the steps are all following the same pattern here.